Hello everyone, nice to have you at the 7th Thermal and Fluids Engineering Conference. I am Shubho Das, MEC Mechanical Engineering student at the Southern Illinois University Edwardsville, and I am presenting my paper on a conjugate Nusselt number correlation for a computer central processing unit cooler. At the beginning, I want to point out the outline of this presentation, which are introduction, model CPU cooler and computational domain, governing equations, the grid study, input parameters, results and applications of the study, and concluding remarks. At first, we want to know what is a CPU cooler. CPU coolers does the job of CPU cooling to maintain safe operating temperature and to ensure optimized cooling performance of the processors. In the picture, we can see a typical computer lab room where we can see lots of desktop computers because our focus is CPU coolers that are employed in desktop computers. And also there are lots of CPU units. If we open up these CPU units, we can find these CPU coolers inside, which are our focus in this study. And several goals of our study remains understanding the design principle of the CPU coolers, exploring the parameters that cause overcooling and undercooling of processors, and eventually obtaining the Nusselt number correlation that will lead us towards understanding the parameters and towards better designing CPU coolers. Now to do so, we need to select a model CPU cooler. We know that there are two main types of CPU cooler out there in the market. One is air-cooled CPU cooler and another one is water-cooled CPU cooler. As we are studying CPU coolers that are employed in desktop CPU cooler, they are normally air-cooled CPU coolers. And we can see a similar one in picture A. Picture B is another similar CAD version of this real CPU cooler. And if we go to picture C, we can see a highlighted portion that is 1/4 of the whole CPU cooler. And picture D is a 1/4 portion cut out of picture C. And the major parts are identified here like base plate, plate fin, and heat pipe. The flow physics remains here like a base plate sits at the top of the computer processor to collect the heat, and the heat is then transferred to the plate fins by means of heat pipes. Two fans employed by the sides of the CPU cooler that are not shown in this picture actually blow air over the plate fins to take the heat away from the plate fins, and this way the plate fins transfer the heat to the surrounding air. The computational domain comes from the previous slide's picture D, where you can see 1/4 of the whole CPU cooler. And in the computational domain, to save our computational time and using method of symmetry, we have just selected only half of one plate fin and half of one air gap as our computational domain. This way we can save a lot of computational time. We can see here the plate fin at the top and air gap at the bottom. Also, we can see enlarged view of heat pipe 1 and heat pipe 2 and the boundary layer mesh around the heat pipes. There are also directions indicating the airflow, air inflow and air outflow. These arrows also indicating air outflow. And two symmetry planes are also shown here and one is here. The governing equation that sets the flow are continuity, momentum, and energy equations for the air, and heat conduction with no internal heat generation for the plate fin. And the assumptions remain steady state, incompressible flow, Newtonian fluid with constant properties. All these equations are written using Cartesian index notation, where repeated index means summation. So the continuity equation in its simplified form is partial I ui equal to 0. We have dropped the gravity effects in momentum equations, and it becomes partial I ui, what should I say? Ui partial I uj is equal to dynamic viscosity times partial I uj minus 1 over rho partial j into pressure term. And in the energy equation, ui partial it is equal to thermal diffusivity times partial I into T. All these equations are written in simplified form. In the energy equation, we have dropped the viscous dissipation term, considering the flow field is laminar. For the plate fin, the heat conduction equation is Laplacian of temperature is equal to 0, and we have considered no internal heat generation. Now we want to execute grid study to validate that the selected domain is ready to give us convergent solution. And we have done this for a range of cell counts from 52,000 to almost 500,000 cells. We can see the increase in mesh size here. At the top, we have small mesh, coarse mesh, and at the bottom, we can see fine mesh. And we can see that the output Nusselt number remains same for this broad range of mesh size or broad range of cell counts. The input parameters remains the Reynolds number from 100 to 2000, heat pipe temperature from 35 degrees centigrade to 95 degrees centigrade, and inlet air temperature is 300 Kelvin for all the runs. I have put two colors of blocks here, one for input parameters and one for output results. The red blocks denotes the input parameters, like Reynolds number remains same and inlet air temperature remains same. Only the heat pipe temperature changes for these runs. And we can see that with the change in heat pipe temperature only, there is no change in Nusselt number. Only change is in the heat rate. This heat rate is calculated using this formula, H times delta T. H is convective heat transfer coefficient. And also from the overall table, we can see that Nusselt number is changed when only Reynolds number is changed. Otherwise, with the change in heat pipe temperature, Nusselt number doesn't change. So Nusselt number is a function of Reynolds number and Prandtl number. Prandtl number is 0.7 for air, which is the working fluid for our study here. And this Nusselt number is calculated using these equations, H1 times diameter of heat pipes divided by thermal conductivity of air. Now, using this table data, we can plot something like this, heat rate versus temperature difference, which shows us that heat rate is a linear function of temperature difference. And this heat rate increases with the increase in Reynolds number only. If the Reynolds number is not changed, the increase in heat transfer is negligible or very minimum. Also, another plot can be drawn for Nusselt number versus Reynolds number, where we can see Nusselt number increases with the increase in Reynolds number. And from these plots, we can draw two correlations like this. The Prandtl number doesn't come in this correlation because it is for year and Prandtl number is 0.7. And we can validate these correlations like this exponent term falls in the range of 0.4 to 0.6, which is a experimentally prescribed range of 0.4 to 0.6 for circular cylinder in cross flow. Also, we have compared our results with another computational study. We can see some deflection, and this is due to some change in geometry, number of heat pipes, heat pipe diameters, and change in flow fields. If we look at the velocity contours, so we can see that Reynolds number, at low Reynolds number, the flow remains skewed and it gets straightened when the Reynolds number increases. And also the stagnation points is little misplaced from the flow direction, but it gets straightened or changes its position with the increase in Reynolds number. And in the temperature contours, we can see that at low Reynolds number, most of the plate area remains hot, and at high Reynolds number, only the area behind the heat pipes remain hot. So better heat transfer is obtained with the increase in flow Reynolds number. Application of the study remains, this study actually allows observing the design parameters of a CPU cooler and discuss their relations. Also, this study has prospects towards investigating the effect of geometric changes in a CPU cooler. And this study allows better design of CPU coolers. The key output remains of the study is are the two Nusselt number correlations, and the obtained correlations are essentials towards designing thermally efficient CPU coolers. Thank you for listening.